Hello, everyone, and welcome to this explainer. Today, we're taking a really fascinating dive into the world of software security. We're zeroing in on a concept that touches, honestly, almost every single modern application out there, but it's still so often misunderstood. We're talking about X.509 digital certificates. While transport layer security, or TLS, is what encrypts the web, X.509 is the literal foundation of trust that makes all that encryption actually mean something. Think about it. Without it, you might have a secure encrypted connection, sure, but you'd have absolutely no idea who you were actually talking to on the other end. I'm super excited to be your host today as we completely demystify the entire lifecycle of these certificates. We're going to follow what I like to call the hero's journey of a simple public key, watching it transform from just a basic mathematical concept into a globally trusted digital passport. And, as a really cool bonus, by the end of this explainer, you'll be completely empowered to eliminate those incredibly frustrating local development security errors. So, let's just dive right in. But first, let me ask you a quick question. Have you ever been working on a project, just spinning up your local environment, and suddenly your browser throws this massive, scary warning page right in your face, telling you the connection isn't private, right? We have absolutely all been there. And what happens next? It usually leads to a frantic Google search and then just blindly copy-pasting some OpenSSL commands into the terminal just to make the error go away so you can get back to work. A lot of developers even end up writing hacky if statements right into their application logic just to bypass TLS during local dev. But man, what happens when that code accidentally makes it into production? It can lead to massive, devastating security breaches. Actually, just setting flags like reject unauthorized false in Node.js to ignore certificate errors locally, that specific thing has accidentally leaked into production environments and literally cost companies millions of dollars in breaches. It's a huge, huge risk. But don't worry, today we are going to learn how to solve this the right way. Okay, here's our quick roadmap for this explainer. First, the certificate lifecycle. Second, step 1, key pairs. Third, the certificate signing request. Fourth, validation and issuance. Fifth, revocation and self-signing. And sixth, your own private CA.
All right, kicking things off with section 1, the certificate lifecycle.
Before we get totally lost in terminal commands, we really need to understand the big picture. Getting a valid digital certificate basically involves 4 main happy path steps. It kicks off with creating a key pair. Then you create a CSR, that's a certificate signing request. You send that request off for validation, and finally, boom, you achieve issuance. This entire end-to-end lifecycle is exactly what governs that little reassuring padlock icon you see up in your browser's address bar. But there is also a fifth, slightly less happy possibility hovering down at the bottom there, and that's revocation. That is the administrative headache that happens when a certificate needs to be invalidated way before it naturally expires. We're going to cover every single one of these steps today.
Moving right along to section 2, step 1, key pairs.
Every single certificate's journey starts right here with a mathematical lock and key. At its core, an X509 certificate is really just a digital container for a public key. So obviously, you can't have a certificate without first having a key pair. This whole thing relies on a brilliant concept called asymmetric cryptography. Think about it like this. Instead of having one single physical key that both locks and unlocks a door, you have 2 mathematically linked keys. You generate one part that stays entirely secret with you. Well, you absolutely must keep it secret. That's your private key. Then there's another part that you can safely share with the entire world, and that's your public key. If someone encrypts a message using your public key, only your private key can decrypt it, period. And conversely, if you sign a digital document with your private key, anyone out there with your public key can verify that it was definitely, undoubtedly you who signed it. That mathematical linkage, that's our hero's origin story. You absolutely need both parts to make the cryptographic magic actually work. So in practice, developers typically turn to a really simple terminal command using OpenSSL to kick this off, exactly like the one here. You just type OpenSSL genpkey, and you specify the algorithm you want. In this specific example from our source material, we're using ED25519. Now, you might be super used to seeing RSA keys, right? They've been the absolute standard for decades. But the thing with RSA is that it requires massive mathematical primes. That means the keys have to be incredibly long to stay secure. We're talking 2048 or even 4096 bits long. ED2559, on the other hand, relies on elliptic curve cryptography. This is awesome because it allows for keys that are a mere fraction of the size, but vastly more secure and just incredibly fast to generate and use. Making our hero key lightweight and highly efficient like this is absolutely the best practice today. The output is then neatly saved to a file named privatekey.pem. And just like that, your mathematical lock and key are officially born.
On to Section 3, the certificate signing request, because a key pair on its own doesn't actually prove who you are.
To really get this, let's use a real-world analogy. If you want to travel and you need a passport, you don't just print one out yourself at home, right? You have to fill out an official application form, attach a verifiable photo of yourself, and hand the whole package over to a government agency. A certificate signing request, or a CSR, is exactly that. It's your digital application form. Remember, a public key all by itself is just raw math. It has absolutely no name attached to it. The CSR is the crucial piece that ties that raw math to a living, breathing human being or a specific organization or a specific web server. You basically bundle up your public key along with a bunch of metadata that proves your identity, and you send it all off to a certificate authority, otherwise known as a CA. So in step 2, we take that freshly generated key pair and we construct our CSR. Our mathematical hero is officially applying for its digital passport. It's a highly formalized request, basically saying, hey, certificate authority, here is exactly who I am, and here is my public key. Can I please have a certified digital passport? When you generate this request in your terminal, OpenSSL will actually pause the process and interactively prompt you to type in real-world identity details. It's going to ask for your country name, your state or province, the locality, your organization name. But most importantly, it asks for the common name. This is almost always what's called the FQDN, the fully qualified domain name. To put that super simply, that is the exact complete web address that users type into their browser to reach you. Something like www.example.com. The CA is going to look really closely at all these details, and that common name, that is the absolute most critical field they will scrutinize to validate your entire request.
Which brings us seamlessly to Section 4, validation and issuance.
Now we're shifting our perspective. Instead of being the developer applying, we're looking at it from the authority's point of view reviewing that application. The certificate authority cannot just blindly trust that you are example.com simply because you typed it into a terminal prompt. I mean, a hacker could easily do the exact same thing. Think of the CA as a deeply skeptical bouncer standing outside an exclusive club. They have to definitively verify your identity and your domain ownership before they ever let you in. According to our source material, they typically use one of 3 very common challenge methods to do this. First up is email-based validation, where they send a unique verification link to a known administrative address, like admin@example.com. Second is HTTP 01. Here, the CA hands you a random, unique token and asks you to host it as a specific text file right on your live web server. When the CA can successfully download that exact file from your domain, well, you've just proven you have admin access to that server. And third is DNS-01, where you have to add a specific piece of text called a TXT record to your domain's backend DNS settings. Because only the true verified owner of a domain has access to the actual DNS provider, this proves ultimate control. In fact, DNS-01 is heavily preferred for automated certificate renewals, like the ones handled by Let's Encrypt, because it can be done entirely through automated APIs without ever having to touch the actual web server itself. Pass one of these challenges, and you prove your identity. And that leads to step 4, which is issuance. If everything checks out and you successfully pass the CA's validation challenge, they take your public key and your identity metadata and they officially sign it. This right here is where the real magic of the chain of trust happens. The CA uses their highly guarded, super secret private key to cryptographically sign your public key and metadata. Then they hand you back a valid, fully functioning X.509 digital certificate. You are officially certified. Our hero finally has its passport. You can now proudly present this certificate to the entire world, and web browsers everywhere will trust it unconditionally simply because they already trust the big CA that signed it.
All right, let's move into Section 5, revocation and self-signing. Because we have to ask, what happens when things go wrong, or when developers try to take shortcuts? Let's talk about the absolute worst-case scenario. Recall that your shiny new certificate is only as secure as the private key you were keeping secret on your end. What if that private key accidentally gets committed to a public GitHub repository? Or what if a hacker actually breaches your server and steals it? If that private key is compromised before the certificate's natural expiration date, you have a massive emergency on your hands. That certificate must be revoked immediately. Historically, you would have to contact the CA and they would permanently add your certificate serial number to this massive, bulky digital do not trust list known as a certificate revocation list, or CRL. And clients would literally have to download this huge list constantly just to check if your cert was still valid. It was clunky. Thankfully, today we rely heavily on a much faster modern alternative called OCSP, which stands for the Online Certificate Status Protocol. Instead of downloading a massive list, your browser just sends a quick, lightweight, real-time ping directly to the CA asking, hey, is this specific certificate still good? If the CA replies, revoked, trust is instantly broken, and the browser throws up a massive security warning. Our hero's passport is officially canceled.
Now, let's pivot slightly. What if you just don't want to deal with a public CA at all? What if you're just building an internal microservice, or you're just testing stuff locally on your laptop, and you want to save the time and money? This is where developers often turn to self-signed certificates. By definition, a self-signed certificate is one where the subject, meaning the person owning it, and the issuer, meaning the person signing it, are exactly the same entity. You are essentially signing and stamping your own digital passport. Now, it's super easy to create one of these using OpenSSL, but there is a massive catch. Remember those scary browser warnings we talked about right at the beginning? Browsers are hard-coded by design to only trust root CAs that are pre-installed by companies like Apple, Microsoft, or Google. When you hand a web browser a self-signed certificate, the browser basically says, I have absolutely no idea who you are, and you're definitely not on my pre-approved VIP list. Because it's not signed by a trusted public CA, it completely breaks that established chain of trust, and the browser throws up a giant red roadblock.
So finally, Section 6, your own private CA.
If self-signed certificates cause tons of errors and public CAs are just way too tedious and slow for local development, what is a modern developer supposed to do? This is where we solve the local host problem for good. Just look at the difference here. Over on the left, we have the typical developer workaround, a standard run-of-the-mill self-signed certificate. Yes, it's fast, but it creates all those annoying browser errors because there's simply no chain of trust. And that directly leads to developers passing reckless flags to command line tools to ignore validation, or worse, writing insecure code hacks just to make their development environment work. But over on the right, we have the elegant professional solution, literally becoming your very own certificate authority. By creating a personal laptop-scoped CA, you can issue certificates that your own operating system implicitly trusts. This completely eliminates all those local errors. And most importantly, it allows you to write your code exactly as it will run in production, with zero bypasses or security hacks needed whatsoever.
Implementing this is actually a really precise, brilliant three-step procedure. Step 1. You use OpenSSL to create a self-signed root certificate. Now yes, the root CA itself is self-signed, but it has special mathematical permissions baked in that allow it to sign other certificates. Step 2 is the most vital part of the whole process. You take that root CA certificate and you install it directly into your operating system's core trust store. To ground this in reality for you, if you're on a Mac, you open an app called Keychain Access, you drag the certificate right into your system keychain and you explicitly set it to always trust. If you're on Windows, you use the Certificate Manager to import it directly into the Trusted Root Certification Authorities folder. And on Linux, you copy it right into your system's Trusted Certificates directory and run a quick update command. By doing this, you are essentially hard-coding your computer to say, hey, trust absolutely any certificate signed by this specific personal authority. Then step 3, whenever you need a certificate for local dev, say for a local Spring Boot app you're spinning up, you just generate a CSR and have your new personal CA sign it. Because your computer fundamentally trusts the CA, it automatically and silently trusts all the local host certificates it issues. It is such a brilliant zero-hack workflow.
So we've seen our simple mathematical key grow up, officially apply for a digital passport, and become a foundational pillar of secure web traffic. Understanding this full X.509 lifecycle doesn't just make you a little better at configuring servers, it truly makes you a vastly more secure and capable developer all around. As we wrap up this explainer today, I want to leave you with a provocative thought to take back to your teams. How does your own organization manage internal trust and certificate lifecycles for local development right now? Are you guys still relying on dangerous, hacky localhost workarounds that could accidentally leak into production at any moment? Or are you actively utilizing private CAs to ensure your code is secure by default from day one? Thank you so much for joining me on this deep dive into the hero's journey of the public key. I highly encourage you to go audit your own systems today, and I'll catch you next time.